right, so it does appear that we are recording. Okay. When we look at our absolute value inequalities, we want to make sure that we are isolating our isolating our absolute value before we actually decompose into the inequality portion. And we said last week that if we isolated the absolute value, and we called this C last week, as long as our constant is positive, then we can go forward with the inequality. If our constant is negative, there are no solutions. So we would also see that in the graph as well, because our graph would not actually cross the x-axis in any location. Okay, so we have to make sure that happens first. And then I am going to make a little note that we want to isolate the absolute value before we move on to the next step. So let's solve the inequality and write using interval notation. We'll first do it algebraically, and then we will move on to graphically. And there's two different ways in which we can do this graphically that I'll show you. First of all, in the absolute value of x minus 1 is greater than or equal to 3, I do see in fact that our absolute value is isolated. I see that we are greater than or equal to 3, and 3 is positive, so that's fantastic. Notice that these are the same setup when we have greater than. The only difference is we just pop that equals to underneath. So they're actually the same thing. There's no difference. One is just greater than, one is greater than or equal to. Once we have it isolated just to the absolute value, we can set the argument, the piece inside the absolute value, set that as x minus 1 is greater than or equal to 3, or x minus 1 is less than or equal to negative 3. At this point, we can add 1 to both sides, and since they're pretty easy to do most in our head, we'll have x is greater than or equal to 4, or x is less than or equal to negative 2. So now that I think about this, what might it look like on a number line? I'm going to put them in order, so negative 2 would come before 4. We notice that they are greater than or and equal to or less than or equal to. So we can include, because it can be or equal to. I want x values that are greater than 4. So values that are greater than 4 would go this direction. And I want x values that are less than or equal to negative 2. So values that are less than or equal to negative 2 would go to the left. Therefore, when I want to write in interval notation, we would again go from left to right, from smallest to largest. We would come from negative infinity all the way until I reach negative 2, which is included because it's greater than or less than or equal to. Hop over, so union, I get to start back over at 4 again, and now I can continue on my way to positive infinity. So all of these are solutions to this particular absolute value. And while we do have a little graph here that can help us, sometimes seeing it in a 2D picture of what's going on with the absolute value function is also useful. So on my next page, I already have the graphs here, the two different ways in which we can graph. Okay. I'm going to look at this bottom one here first, because notice I put this exact same function. I didn't change anything inside. I just put exactly what was stated on the problem without moving anything. The only thing I don't like about this strategy in Desmos is that, yes, it does. Notice it gives me a solid line. So it tells me that it's included. We will see in a future example a dashed line for exclusion. The only thing is, notice here I don't have any of these nice gray dots that Desmos gives us when it crosses. So while we do know that this point here is in fact -2. So we know this is the point -2, 0. And this is the point here 4, 0. We don't actually have the dots that we can click and actually showcase what they are. But what we do have is the shading. So here I see that we're coming from -infinity all the way until I reach -2, hop over, and then I start again at +4, and then I get to continue on to +infinity. So I like this strategy by putting in the inequalities because I can actually see the shading. However, what if these points are not nice whole numbers that I can actually count on the graph, and they're ugly fractions or decimals that aren't easily navigatable into nice fractions, if you will, okay? That's why I also like this strategy here. I'm going to ultimately, I'm going to put in quotation set equal to 0 is ideally what I'm doing. So all I did was subtract 3 from both sides. So when we look at our original equation, I just set it equal to 3. And now I'm going to see, now I've got my v for my absolute value. I want to know, where is my graph greater than or equal to 0? Well, my y values are greater than or equal to 0 over here and over here, right? So my y values are greater than or equal to 0, coming from -infinity all the way until I hit here. Notice now they dip below the x-axis, so they're negative down in this area, which is why we have to skip over that part. And then we pick back up and go from 4 to infinity. They tell the same story, just in a different way, especially if we want to get these specific points, or you'd prefer to actually see the graph look like an absolute value graph instead of an inequality graph. We're going to show you both of these throughout all of our examples, and you can choose which method you prefer. Okay. Our next example is 4 minus 3 times the absolute value of 2x plus 1 greater than -2. Here, our absolute value is not isolated, so we do need to isolate that first before, because right now this is a negative number. We can't have a negative number here, but maybe when we isolate, we'll be able to find a positive number. So I'll first subtract 4 from both sides. Now I have -3 times the absolute value of 2x plus 1 greater than -6. Then I'll go ahead and divide everything by -3, and I'm being dramatic here. I know you could do that in your head, but don't forget, when we divide or multiply by a negative, our sign changes or flip-flops, giving us 2x plus 1, the absolute value, is less than 2. Now that I have less than, we can use this situation where my argument is in the middle. So my argument is greater than the negative version of our b and less than the positive version. Setting this up, I'll have -2 less than my argument is the 2x plus 1 less than +2. Now our goal is to get x by itself. We really have two different inequalities here, so I do need to subtract 1 from everything. This gives me -3 less than 2x less than 1. And then we divide everything. We're dividing by a positive, so that doesn't change the direction. So I have -3 halves less than x less than half. So when I think about our number line here, -3 halves is in fact smaller than 1/2. there's going to be open circles at both of these locations because they're less than symbols, they're not equal to, and our x values have to be stuck in between here. X values have to be stuck in between here. So when we write this in interval notation, we'll have -3/2 to +1/2 with parentheses, because we know parentheses means it's excluded. Looking then at the two different types of graphs we can have, I started off with the graph. I didn't change anything. I didn't move. I just copied and pasted exactly what the original function said. I notice now that I am shaded in between, but I don't specifically, might not know what these two specific points are because there's not nice gray dots that we can choose. But we do know that this is in fact -3/2, 0, and that this is in fact, oops, I should have open circles here because they're dashed lines, and 1/2, 0. Again, I noticed the dashed lines because it's greater than. It's not equal to, so the lines are excluded. And I see that I am shaded in between here, which tells me, I'll put parentheses here, that my x values have to be in between these two values. Now, what if you wanted to do the other way because you wanted to know what specifically those points were, right? What I did was I just added 2 to both sides, so setting it equal to 0. And in my mind, I'm not putting greater than 0 in my decimals. I'm just thinking, I need all of this. Where is my y values greater than 0? Here it gives me these nice x value points. I know that they are excluded, even though it doesn't exclude them in our graph. But notice that our y values are greater than 0 in between here. Right? Down here they're negative. We want ones that are greater than 0. If this had been flip-flopped to less than, then of course we'd want the other options. But here we want them, where are they positive? They're positive in between those 2 points. This next one is pretty interesting because I'm setting up an inequality with my absolute value before I'm actually solving anything. But in this particular case, I have 2 different inequalities. I have the inequality where 2 is less than x, the absolute value of x minus 1, and I have the inequality of the absolute value of x minus 1 is less than or equal to 5. And in which case, I'm going to separate these two because they might be treated a little differently based on if it's less than or greater than. So this first one, I'm going to set it up as 2 less than the absolute value of x minus 1. And then I'm also going to set up the inequality of x minus 1 is less than or equal to 5. And because my brain might work a little differently, it's easier for me to have the absolute value on the other side. So I am going to rewrite this as the absolute value of x minus 1 is greater than 2. This way, when I look at my requirements, if I am greater than, I know, and 2 is positive, once x minus 2 is x minus 1 is isolated, then I can set this equal to our argument is greater than 2 and our argument is less than -2. But over on the right hand side, I have less than or equal to, so I need to set it up with the argument in the middle. So I'm having lots of interesting things happen here. So I'm going to start off by putting, just working with this absolute value of x minus 1 greater than 2. I'm going to set this up as x minus 1 is greater than 2, or x minus 1 is less than -2. I can add 1 to both sides. So x is greater than 3, and then if I add or, x is less than -1. We'll graph them here in a moment so we can see what's happening. But then I've got this x minus 1 is less than or equal to 5. So I know I need to set this up with -5 less than or equal to my argument of x minus 1 less than or equal to +5. And then adding 1 to all pieces. So if I add 1, I'll have -4 is less than or equal to x less than or equal to 6. Let's put this on a graph, and I'm going to put my numbers from least to greatest. So the smallest number I have is -4. This can be included. My next smallest is -1. This will be excluded because it's less than, not equal to. Then I'll have 3, which is the same thing, open circle. And then I have +6, which can be greater than or equal to. So far, I'll start with this guy here. My x values have to be in between -4 and 6. So my x values have to be in between here and here. But also, we have to take into consideration these inequalities. So my x values also have to be greater than 3. So if all my x values greater than 3, go this direction. All my x values also have to be less than -1, so going this direction. So there is a place of overlap. That overlap, where these inequalities overlap, is in between these two values and these two values. That is where our solution lies. I cannot have a value of -5 because -5, although is less than -1, -5 is not in this range here. Okay. So my solution set is going to be from -4 to -1, and I'm using a parenthesis here, so -4 included, -1 excluded. I'm going to hop over that middle part. I can start back at 3 again, which is excluded, and then I can go to +6, which is included. Let's look at what the graph appears. So in my graph, I did decompose the larger inequality into the two separate ones. So I've got the 2 is less than the absolute value of x minus 1. And I have the absolute value of x minus 1 is less than or equal to 5. Notice I do have my values that are excluded with the dotted line here. Again, it doesn't tell us, but we do know that this is the point -1, 0, and this is the point 3, 0. I also know that the points on the solid lines, of course, are -4, 0, and 6, 0. Now when I'm looking for the shading, I'm looking for the shading that's overlapped. Now if you were to graph this in Desmos, you would have maybe two different colors and you're looking for that overlap. We can see that overlap because it's a darker gray than the other locations. So the darker gray is where they're overlapping. And they're overlapping in between -4 and -1 excluded, hopping over a bunch, and we're starting at 3 to +6 included over on the right hand side here. So just in between those two locations. So I like that visual aspect of seeing these overlaps that we talked about when we graphed on our number line. Now another alternative, of course, is to quote unquote set equal to 0 so that we can identify where we are greater than or less than. So I set our first one, the absolute value of x minus 1, and I subtracted 2 from both sides. So if I subtract 2 from both sides, I'm looking for where the absolute value of x minus 1 minus 2, where that's greater than or equal to 0. Okay, and the line at which that's happening is this particular line because it has that negative 1 and 3 that we had found. Okay. And I see that our graph is greater than or equal to negative 0 over on like this side, right? Greater than 0 over here is where those y values are, because look at the graph here. Okay. Now when I solve and simplify for the bottom one here, I subtracted 5 from both sides, and in this case I want to know where is this graph less than 0. Or equal to, I should say, less than or equal to 0. So where is my graph negative for this? So when I look at the second graph with negative 4 and 6, where is this graph negative? Well, this graph is negative down below here. So we're combining the positive version for this graph and the negative version for this graph, and we say that those are happening in between these 2 points. So sometimes the point part can be used in tandem, I think, with the graphing portion, as it will make our life a little easier. This might help us find the specific locations where this might help us with the graphing or the shading part, if you will. All right, and our last one, because our brains might be getting a little hurting so far. So we'll just, this is our last type that you might see in your MyOpen math homework. We've got the absolute value of x plus 1 is greater than or equal to x plus 4 over 2. So notice on the right hand side I have x over there. We're going to assume that x must be positive, otherwise we're not going to be able to solve, right? Because we have to say that this b portion is positive in order to follow along. We have a greater than or equal to, so then I can set it equal to the positive version and the negative version of this, since our x plus 1 is already isolated. So the first thing I'll do is set x plus 1 greater than or equal to x plus 4 over 2. And then I'm going to say or. I also need x plus 1 is less than or equal to the opposite of x plus 4 over 2. I'm going to tackle this left side here first. I'm going to multiply by 2 so that I can undo the fraction. And then distribution gives us 2x plus 2 is greater than or equal to x plus 4. I typically want to keep my x value positive, so I'm going to subtract x and then subtract 2. Giving me x is greater than or equal to positive 2. Similarly, I'm going to do the same thing on the right-hand side, but first I'm going to distribute the negative into my fraction, if you will, giving me x plus 1 is less than or equal to negative x minus 4 over 2. I can do the same thing where I will multiply both sides by 2 so that I can undo the fraction. Distributing, we have 2x plus 2 is less than or equal to negative x minus 4. I can add x this time, giving me 3x plus 2 is less than or equal to negative 4. Of course, subtract 2. Ooh, I could have done that at the same step. 3x is less than or equal to negative 6. X is less than or equal to negative 2. So when I think about my number line, I have negative 2 and I have positive 2. Both are included because it's greater than or equal to or less than or equal to. My x values have to be greater than 2. And here our x values have to be less than or equal to 2. So our inequality, I'm going to come from, or excuse me, interval, negative infinity to negative 2 included. Hop over that middle, I get to start back up again at positive 2 and go towards positive infinity. I apologize that I've got this little, I don't know where that come from, but I wrote the equation, the function, just as it says here, up above here. And I do see that the nice shading happens. We can count the number of lines here, so I know that this is 2, 0, and negative 2, 0. And I do see, since it is a solid line, that I am shaded to the right and to the left of these lines. It makes it nice and easy. Now, if I want to set this equal to 0, all I did was move that x plus 4 over 2 to the left-hand side. And I'm looking for where on my graph are my y values greater than or equal to 0. So I've got my negative 2 and positive 2, which we had already talked about. And notice our graph is positive over here and above here. And it stays positive to the left and to the right of these values. So that shading also comes into play, where we have to think, where are our y values greater than 0? We can see that happen to the left. We can see that happen to the right. It is negative in between here because our graph dips below the x-axis. So perhaps using both of these graphing tools, both of these methods will be useful. Maybe this one will be useful for helping you determine what those x values might be. And then this strategy will help you with determining where we need to shade in conjunction with the algebra. So all kind of the 3 pieces put together. Okay. That takes care of the first half of the notes. We will do quadratic function inequalities separate.